Thanks for the intro. I was asked to give a talk, a background talk, actually, for Effie's talk later this afternoon. So maybe I'll start by advertising that. We're going to be talking about different things, but I guess some of the techniques that Effie is using in her research she's going to speak about later are similar to techniques that Dave Feuder and I used in a paper that we wrote a few years ago. So as background to Effie's talk, I'm going to introduce a lot of this machinery and some of these techniques, in the context, I guess I'll be explaining this research that Dave and I did about 10 years ago. So so this is joint with Dave Feuder about 10 years ago. So this is so this is yeah, right. A unique.
Part of an RDU you're in,
Right.
right?
So what I'm going to do today, this talk has basically 3 parts. I'll put the outline over here. I know that you guys can't see it so well, but so part 1, I want to spend a little bit of time. The manifolds that we're going to be looking at are not complements today. And so I wanted to describe a couple of different decompositions of not unlinked complements into polyhedra. So what we're going to do, we're going to start out with this complicated manifold, which is a not or a linked complement, but we're going to chop it into extremely simple pieces. And these are just balls with extra information. So polyhedra. Second part of the talk is we're going to put a little more structure on the polyhedra. So angle structures, or angled. And then we're going to be examining surfaces which sit inside of them. And so this is going to give the surfaces a combinatorial area and a combinatorial length of slopes. OK, and then the third part that I'm going to kind of try and do throughout is examples and applications. OK, so that's the plan. I'll start with this board. OK, so for part 1, throughout K in S3 is going to be a not or a link. And I am interested in topological and geometric properties of the manifold S3 minus K. And sometimes I will refer to this as M. So M for manifold. And we are going to cut this into polyhedra. So a polyhedron, let me just say. So what do I mean by this? I mean a ball with extra information on its boundary. So each vertex or ideal vertex has valence greater than or equal to 3, and each edge OK, so sometimes, I guess what I'm trying to say here, sometimes a polyhedron is just a graph on the boundary of a 3 ball, but we're going to restrict to graphs with these 2 properties. So no edges, or no vertices like that. Just turn that into a single edge. And every edge has endpoints on a distinct vertex, so no loops in our polyhedra. OK, so those are the only 2 requirements. OK, and we are going to view. So here's a first decomposition of this manifold S3 minus K into ideal polyhedra. So this first decomposition is due to Manasco. And then following ideas of Thurston. So what Manasco does is you view your knot or your link as sitting on, let's see, let me draw a knot. Okay, so here's a knot sitting on a projection plane. Okay, so K is going to be sitting on some S2. All right, so you've got your projection plane is this thing this parallelogram I've tried to draw. And you thicken it up just a teeny, teeny, tiny bit. The knot's going to sit in this region where, so over crossings it's going to go up a little bit, under crossings it's going to go down a little bit, but everywhere it's going to stay in this well-defined S2 sitting inside of it. So this is a projection plane. And then the Manasco decomposition says you think of this plane separates S3 into two balls. So there's a ball above and there's a ball below. And those are your polyhedra. Okay? Okay, so you need a little bit more information on how to glue these together. But so the polyhedra there's a ball above and the ball below. And so when you can think of expanding a balloon above and expanding a balloon below, and when they meet, they're going to meet in faces. So let me label these faces A, B, C, D, E, F. And the regions, so the faces are going to correspond to regions of the diagram. And then how do you get an edge? Well, you'll get an edge when two of the faces bump into each other. And they're going to bump into each other at crossings. So right here, for example, there's going to be an edge between face E and face B on this polyhedron that's coming up above. So right up above, you're going to be bumping into this face E. You're going to be bumping into this face B. And then they're going to be merging into this pink line. And that's going to give you an edge of the polyhedron. So edges are going to lie on crossings. They're often called crossing arcs. And then the vertices are the remnants of the knot. And in fact, they're going to correspond to overstrands. So a single overstrand is going to give you an ideal vertex. Overstrands in the top, understrands in the bottom. Okay, and all of the vertices are ideal. Okay, so this gives you a way of breaking a knot into polyhedra. And if you think about this for a long time, you can see that there are actually a lot of nice properties of this, particularly in the case that your knot diagram happened to be alternating. This is a nice polyhedron. I wanted to spend a little bit more time, though, on a different. So this is the first decomposition of a knot into polyhedra. I want to talk about a different type of polyhedra that I think is a little bit more visual, a little bit more geometric as well. So this will be one example that we'll play with. We'll have one more to work with as well. OK, are there any questions on this so far? It's hard to know what everybody knows and doesn't know. OK, so if this is your first time seeing that, that's probably fast. If you've spent many years thinking about this, then I'm probably going too slow. And there may be somebody in the middle, but I don't know who you are. OK, so. So the next decomposition I want to talk to is a decomposition of a very special type of link into ideal polyhedra. And this decomposition I learned about from Ian, Agel, and Dylan Thurston. And this is for a type of link called for fully augmented links. OK, so what is a fully augmented link? This is where I have to start. A fully augmented link, this consists of different types of components. So there are two types of components. So the first type, there are components which lie entirely in the projection plane. OK, so we've got our projection plane as before, and there are some components which just sit in here. And then the other type are what I call crossing circles. And these are perpendicular, so orthogonal to projection plane. And it's a simple unknotted component. So here's the projection plane, right? It's orthogonal to that. And exactly two strands of the link run through it. So maybe let me kind of draw a picture like this. OK, so in this picture, if I were to put in some crossing circles, maybe here's one here, one over here. OK, so this would be an example of a fully augmented link. And then you can actually extend this a little bit. So the first component's either embedded in the projection plane, or you can actually allow a single crossing right at a crossing circle, or a single crossing, like so. OK, so fully augmented link, I'm describing this way. And we're going to decompose these into polyhedra, to ideal polyhedra. So in the following way. So decompose OK, so the first thing you're going to do is view each of these crossing circles as bounding a disk. So a crossing circle bounds a crossing disk. And this is going to be a shaded face. These are going to give me shaded faces when I'm all done. So for every one of these little crossing circles, I'm going to shade this in. And then I'm going to cut along it. OK, so just, you can think of this is a full slice of pita bread. And I've sliced it down the middle. So it's open inside. So you can kind of push it apart from itself. OK? When you do this, after you've cut along it, notice that you can undo single crossings. So if I think of this, so side view, I've cut along this crossing disk, and so I've separated these strands from each other, and I have this bit of thing in between. I can rotate one half of it along its boundary here, and add or remove a crossing, and what I'm going to get is going to be homeomorphic. Okay, so undo single crossings at this step. So from now on, I'm just going to think of everything as really being flat in the projection plane.
Why can't you only rotate once? Like, why not do as many crossings as you'd like?
You could, but that's going to make things more complicated. So the easiest way to do this to visualize is just to get rid of any crossings that you have. So you may have single crossings. I mean, OK, so this link is going to be homeomorphic to put as many even crossings in as you want, actually. But the complement of the link, I'm sorry. The link complement, you can put as many crossings, or you can twist a lot. You can put in as many twists as you want. So that's pairs of crossings. But the whole thing will be homomorphic to either 0 crossings or 1 crossing. And then at this stage, to make things simple, just undo single crossings. OK? OK, other questions? OK, so step 2 is you cut the whole thing in half along the projection plane. So now you have, so everything is embedded in the projection plane. You're going to have a top half, and you're going to have a bottom half. So slice along projection plane. OK, so you now have 2 polyhedra. One of them looks like something like this. OK, so here are your link components. They look something like that. And then you have these little bits of shaded surface that are coming kind of up, like so, right? And then down here, you're going to have something similar, only it's going to be underneath. Right, and then you've got your bit of shaded surface doing something like that. OK? Is that picture OK?
Sorry, when you say undo single crossings, you mean like a half twist?
Half twist,
You're
yeah.
actually undoing a half twist.
Yeah, that's right. Undo a half twist, yeah. So you don't have any half twists. It's changing. It changes the gluing when you put these things back together. But at this stage, when you slice here, you can just do whatever twisting you want, half twists or full twists. OK. OK, step 3. Let's flatten things that look like this. So your crossing circles become something like this. And then I guess, well, I wrote this as a separate step in my notes, but just collapse the remnants of the link to ideal vertices. OK, so so this is a remnant of one of these crossing circle links, so it becomes a single ideal vertex. These guys become single ideal vertices. And what you're going to see is your link complement, your polyhedra. You're going to have 2 polyhedra with lots of shaded triangles. You're going to end up with a 4-valent graph, checkerboard colored, with these shaded faces coming from your crossing circles, and with these, I would like to call them white faces, coming from the projection plane. OK? Works better on a whiteboard to call them white faces. But. So let's do an example really quick. OK, so here is a fully augmented link. And so my stages are, first I'm going to shade crossing disks. And I'm going to cut through those and unwind. So, oops. When I cut and unwind, I can kind of, well, let's do this in 2 steps at once. And I should maybe, let me maybe use a different color for these disks. I'm going to see OK, so when I cut along the crossing disks, I unwind the half twists, and then I'm going to cut along the projection plane. And what I'm going to see is going to look like this. And now I shrink all of the white lines here to ideal vertices. And so I'm going to have, well, there are going to be 3 vertices in the middle coming from these crossing circles. But then there are going to be 1, 2, 3 others on top. So, and 3 on the bottom. Let me show you how you connect these. Basically, so this is the easiest one to draw. So this face becomes something that looks like this. And then this face becomes something that looks like this. Okay? This triangle has, there's an edge from here to here. There is this stripe just goes now around an ideal vertex, so that doesn't go very far. There's an edge from here to this other vertex over here, and then there's an edge connecting like so. So we get a triangle that looks like that, right? And then one over here, one over here, and one over here. Okay, so this is one of the 2 ideal polyhedra that make up the complement of this link. The other one is identical to that. Okay, any questions? All right. Is that guy an easy one? You would get exactly the same picture, whether the half twists are in it or not, yes. All that the half twists do is they will change the identifications on these. So if there are no half twists, I would glue these 2 triangles together, like that. If there's a half twist, I would flip one of them over and glue to a guy in the back.
Are you asking seriously or just knowing?
Well, it
So-
looks like it's 2 octahedra.
It is, yeah. It's 2 octahedra on top.
Okay, well, I'm guessing that it's about 2v8. Okay. All right, so part 2. So let's put a little bit more structure. So angle structures and combinatorial area. Yeah, so I mean, you can ask questions about these things. They're very, very nice. They have very nice hyperbolic geometry on them. But for purposes of this talk, you don't need to know all of the hyperbolic structure on these guys to determine information. We're just going to look at combinatorial areas and lengths using angle structures. Okay, so all right. So in order to put an angle structure on these things, the first thing I guess we're going to do is I need to be able to talk about truncated vertices. So all of my vertices in both of these. Where did they go? This one, this Monasco decomposition, and in these fully augmented polyhedra, all of the vertices are ideal. So let's truncate ideal vertices. Okay, so we have an ideal vertex going off to infinity. All of my ideal vertices are 4-valent. I'm just going to decide we're going to chop it off somewhere and turn this into a face. So the edges get shortened. And we add an extra face right here. So this is called a boundary face. We add these extra edges, which I will call boundary edges. And so this gives me, instead of an ideal polyhedron, now I have a finite polyhedron. And then these guys that are left over will be called interior edges. So these were original edges. Okay. So here's Monasco decomposition. Okay, so now we're going to talk about a normal disk sitting inside of the polyhedron. So a normal disk, D, inside of the polyhedron, this is defined to be a disk whose boundary is a normal curve, which is kind of a useless definition. So let me define a normal curve. So a normal curve sits inside of the, so the boundary, right? The boundary is in the boundary of the polyhedron. E is a polyhedron. And it satisfies the following properties. So number one, we're going to make sure that it's transverse to edges. Okay, so if I have it, these are basically, you want to think of these items as things that you do to your disk if it's not in a good position to begin with. So if it's not transverse to the edges, just bump it a little bit, and now it will be. So transverse to all the edges. Two, it does not lie in a single face. So if the boundary of your disk is in a single face, right? So here's your polyhedron, here's the boundary of your disk, the disk is doing something, and here, da-da-da. You would naturally want to simplify that by doing what? Let's push it through, right? So none of this. So you can't have the boundary in a single face. Endpoint, so no arc of gamma has endpoints on the same edge or an interior edge and adjacent boundary edge. Okay, so what's the picture here? If your arc has endpoints on the same edge, then you would want to push that through that edge, reduce the number of intersections. If you have an endpoint on, let me truncate the vertices a little better. If you have an endpoint on an adjacent boundary edge and an adjacent interior edge, then again, you want to slide that past and reduce the number of intersections. Okay, and then there are two extra conditions. Gamma meets each edge at most once. And meets each boundary face at most once. Okay, so now we're ready to talk about the definition of an angled polyhedral decomposition. So an angled polyhedral decomposition of a knot of S3 minus K, this is a subdivision of your link complement into ideal polyhedra. And then we're actually going to truncate it, or truncate them, such that each interior edge is assigned an angle between 0 and pi, and It's also assigned, so it's assigned an angle and an exterior angle. So this is really just for notational purposes. You take pi minus alpha I to be the exterior angle. Okay, and these must satisfy such that. Okay, 1. If you sum up all of the angles around an edge, you get 2 pi. Okay, and then the second condition is if gamma is a normal curve, meeting only interior edges, then when you sum up the exterior angles that meet gamma, you always get something that is at least 2 pi, and you get if equality with equality, if and only if gamma encircles an ideal vertex. Okay, so this is the definition of an angled structure. Let me give you an example. So let's take this example. So here is, so let me erase. The link complement that I just erased has a decomposition into 2 polyhedra that look like this, right? So what I'm going to do, I need to assign, first I need to assign an angle to every one of these yellow edges that I see. So think of these dots are going to be truncated, and they're going to be squares. So here are my truncated boundary faces, or what these are called. Okay, just 3 more. 1, 2, 3. Okay, so there's my truncated polyhedron, and I'm going to assign all edges to be angle pi halves. Okay, so now we need to check that this is really an angled structure. So around any interior edge, I need the sum of the angles to be 2 pi. Well, okay, so like this yellow edge here, every time that it appears in the polyhedron, when it's glued to other edges in the polyhedron, they must all, the sum of all those must be 2 pi, right? So this edge here is glued. In the case of the twisting, remember we have 2 polyhedra that look like this. Well, okay, maybe the right picture to draw is this one. All of my edges lie on the intersection of these white faces and these crossing circles. And where are they? Well, they're here, here, and here. So here, right here, here, and here, 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 and here. Each of these edges is 4-valent. It meets a yellow edge, or yellow face above, a yellow face below, and it meets a white face in this direction and a white face in this direction. So because every single one of these, so this is 4-valent, this one, same thing. We have above, below, white face, and then above, below, white face, white face. Every one of my edges is 4-valent, and so that means that the first condition holds automatically. Right? So all edges 4-valent implies that item 1 holds. Okay, the second condition is a little bit trickier to check. So for 2, you need to check every normal curve that meets only interior edges, the sum of the exterior angles is at least 2 pi with equality if and only if it encircles an ideal vertex. So this is basically saying something about the number of edges that your normal curves will meet in this case. And so you can check that, in fact, any normal curve is going to be meeting at least, any normal curve that meets only interior edges meets at least 4 of them. So check normal curves meeting only interior edges. It meets at least 4 edges. If it meets only 4 edges, then it's running around a vertex, like so. And otherwise, it will have to meet more. Okay. So I guess this is using too some assumptions on the original knot that you started with. So for example, you're going to want to start with a diagram that's prime is going to be required, and some other assumptions on the knot in order to make sure that this happens. So this is right with some assumptions. So prime diagram. Something that's called twist reduced. Okay, but that's all that you need in this case. Okay, any questions?
So you're saying that's only, does it work for, say, non-trivial satellites that are prime, or do they really have to be hyperbolic?
Well, by the time you, if you start, okay, so often I describe these fully augmented links as you draw these pictures and you put in the augments. Usually, what you do is you start with a knot, and then you augment and then you untwist. When you do this maximally, then in almost all cases you're going to end up with something hyperbolic. There are only 2 cases that avoid this. That would be if the thing you started with didn't have a prime or twist reduced diagram. But otherwise, you'll end up with something hyperbolic, even if you started out with a satellite, because every time you have a crossing, you're going to be putting in one of these circles, and you're going to be ruining all of the nice annuli and cipher fibered things you would be seeing in there. Yeah. Yeah, good question. Other questions? Okay, so let's talk about combinatorial area now. So we're going to be looking at surfaces which are sitting inside of link complements. Okay, so let's take a disk. And I think that let's start out with normal disks. So D normal. This can be generalized to more complicated disks, but I think for the purposes of this talk, all we need are the normal ones. So so if you have a disk sitting inside of a polyhedron, so the same truncated ideal polyhedron, and the boundary of your disk, so meet some edges. So let E1 through En be the interior edges met by the boundary of D with E1 through En, the corresponding what did I call these? Exterior angles? Okay, then we're going to define the combinatorial area of the disk to be the sum of these exterior angles plus pi times the number of intersections with your boundary with boundary faces, is what I should call that, boundary faces. Okay, so when you hit And interior edge, you pick up an angle. If you run into one of these boundary faces, then you're going to pick up area pi. And this actually, so this the intuition, this comes from hyperbolic geometry. So minus 2 pi, yeah, I'm sorry. Minus 2 pi when you're done. This is exactly the formula for hyperbolic area. Formula for hyperbolic area of a polygon. Okay, so if it's got an ideal vertex, then it picks up pi minus 2 pi, right? And then and then the sum of the exterior angles plus ideal vertices minus 2 pi is going to give you the total area of a polygon. Okay, so let's look at a couple examples. So these are two special types of faces. So okay, so I have my polyhedron doing something. Here is a disk in orange. It's meeting two boundary faces and no interior edges. And so the area of this guy is going to be 0 plus 2 times pi minus 2 pi is 0. So this is a 0 area disk. Okay, this is called a boundary bigon. It has, right, because the disk, it has 4 sides, but only 2 of those are in interior faces. Okay. And then another one, let me just draw it on top of it. Another example would be a disk which runs parallel to a boundary face. This is this green thing. So a vertex length. Okay, this one also has area 0, and that's by our condition, our definition of the angled structure. Okay, so okay, it looks like I do actually want to extend this definition of the combinatorial area to what are called admissible disks. So extend definition to admissible disks. So admissible disks, these are similar to normal, only you allow them to be immersed. So you no longer require that they're embedded anymore. And then the boundary is a curve, satisfies. So my definition of normal is probably gone at this point. Oh no, here it is. Okay, so the boundary still is transverse to edges. It still doesn't lie in a single face, and arcs don't have endpoints on the same edge or interior edge and adjacent boundary edge. So this is still true. And also each segment in a face of boundary of P is embedded. Okay, and then an admissible surface this meets each polyhedron in admissible disks. Okay, so this is a lot of combinatorial data to keep track of. Let me just say, okay, so let me give you a reason to think that this might be something useful to study. So we have a Gauss-Bonnet formula. So if you have an admissible surface, then the area, the combinatorial area of F, this is defined to be the sum of the areas over each disk. This is going to be equal to negative 2 pi times the Euler characteristic of that surface. Okay, so as usual. Okay, but I also want to say something about lengths of slopes. So let's suppose you have a disk, D in P, with its boundary meeting at least one boundary face. And let gamma be an arc on a boundary face. Then we define the length of gamma with respect to D to be the area of D divided by the total number of arcs of BD on boundary faces. Okay, so I'm going to use this to say something about lengths, combinatorial lengths of surfaces embedded in knot complements. So these are going to be essential surfaces, and we're going to be looking at boundary slopes, basically. And I want to say something about the slope lengths of these boundary curves. So the combinatorial length so the combinatorial length of gamma, we're going to let H be the union of admissible disks Okay, so given a curve, we want to define a length of this curve. So we're going to take an admissible surface whose boundary is the curve, and we're going to define the combinatorial length of gamma to be the sum of the lengths of the gamma I with respect to the di, and then we're going to take the inf over all h. So given a curve, look at all possible admissible surfaces whose boundary is this curve, sum up their lengths, and then take the infima. And we're going to apply this to lengths of slopes. So if SI is a slope on the boundary of our manifold, so this is, we're looking at a link complement here, right? And so this is a torus. So a torus boundary. Then the length of this slope, the combinatorial length, is defined to be the infimum of the combinatorial length of gamma, where gamma is any multiple, non-zero multiple of S. Okay, looking at the clock, I better say something interesting in the next 5 minutes. OK, so here's one thing that was proved by Mark Lackenby. He showed that if you have a manifold with an angled polyhedral decomposition, and you have a collection of slopes, so M with angled polyhedral decomposition, and you have a collection of slopes on their boundary, and the length, the combinatorial length of each SI is strictly greater than 2 pi for all I, then the manifold obtained by Dane filling, so MS1 through Sn, this is the Dane filling, this is going to be hyperbolic. Okay, so using this combinatorial notion, adding up areas and summing, you get this result. That's a hyperbolic Dane filling result, provided that your combinatorial lengths are greater than 2 pi. Okay, so we want to apply this. So maybe let me just end here. With these polyhedra from the fully augmented link decomposition. So remember, we're going to assign, so it's this board over here. We've assigned every angle to be pi halves. And so exterior angles are also pi halves. And let's see, where did it go? OK, so this leads to a theorem by Dave Feuder and I, which says that if you have another link with at least 6 crossings per twist region, then your knot complement is going to be hyperbolic. Okay, so here's an example of something that we can use. So OK, so let me say something about the proof. 6 crossings per twist region. A twist region looks like this. It's where 2 strands of a knot cross around each other maximally. The way that we prove this is we augment this link. So put in one of these crossing circles, and then untwist. And you're going to get, if you do this at every crossing, you are either going to get a flat, fully augmented link, or you may have 1 crossing per twist region. This guy has an angled polyhedral structure. But we know how to go backwards from here to the original guy. So let me take this out. So to go from the one to the other, you do a 1 over n Dane filling on this orange circle, crossing circle. OK, so we have the augmented polyhedral structure. We have slope lengths, slopes to go back to our original link. And basically what we need to do, and so then the step that's more complicated, not too complicated, but we don't quite have enough time to go into the details, is basically we show that each of these 1 over n curves has combinatorial length strictly greater than 2 pi, provided there are at least 6 crossings in each twist region. Okay, so the n depends on the number of crossings that you begin with. So OK, I will stop there. Thank you.